All right, so we've been talking about, we did an activity on scatter plots and on lines of best fit, so we're going to dive a little bit deeper into that now. So 4.4 and 4.5 is when we're talking about finding lines of fit, then also analyzing what each of those means. So we have quite a few vocabulary words to go over. First one is residual. So what a residual is, it's the difference of the actual y value and of the corresponding y value found using the line of fit. So what we're doing is we're taking the actual value and subtracting the estimate from that. And when I do that, what I want is for this value to be close to 0. And I'll kind of show you what I mean. Let me do this maybe. Okay, so here is, I'll do it down here, I guess. Okay, so if this is my graph like this, and I have some data points here, we'll just throw some random ones. Got a positive linear correlation here. And my line of best fit looks something like this. Okay. My line of best fit's not going to go through all of my points. And what regression does is it looks at, well, okay, this is my line of best fit. Let's look at like this point. I'm going to use this. Like, so if we look at this point right here, I want to look at how far away is this point from the line, right? So what residuals are is they have you look at the actual data point. This is my actual data point. And I want to look at, well, what's the difference between my actual data point and where I estimated that it would be up here, right? So I go through and I look at the difference between those two things. And it makes sense that I would want it to be close to 0, right? Because, like, for example, this point down here lies on the line, and so my actual value minus my estimated value is going to be 0 because they're the same thing, right? So that's kind of what I'm looking at, and we'll have some more examples of that later, and it'll make some more sense. So it's my actual value minus my estimated value. We also do something called total residual. And my total residual, right, is just when I add them up. So add residuals will give me my total. I also want this to be as close to 1 as possible. Because if this actually is a good representation of my data, when I add up my residuals, they will also be close to 1, and we'll do an example of that also. So up until this point, we've been figuring out lines on our own. We've been calculating lines, we've been writing equations for lines by ourselves. So the next term is linear regression. And linear regression is a method that graphing calculators use to find a precise line of fit that models a set of data. So up until this point, we've been figuring out equations of lines on our own. Now, we are going to let the computer do it for us. So that's what linear regression is. Linear regression is just me saying, or telling a computer what to do, and it's going to spit something out at me. It's going to spit out an equation in the form y equals mx plus b. And we can look at that later too. We'll see an example of that as well. The next one then is the line of best fit, or the line of fit. The line of best fit is the line that fits the data the best. Linear regression produces this. Okay, so when linear regression is done, it's going to spit out a line in the form y equals mx plus b. That equation is our line of best fit. Okay, so next we're talking about the correlation coefficient. We talked about how graphs can have strong or weak correlation. And so our correlation coefficient is an R value, is what we call it, and it tells us how closely the equation of a line of best fit models the data. In other words, how strong or weak is our correlation. And our R value is going to spit out a number between -1 and +1. Okay, my correlation coefficient is going to lie somewhere between -1 and +1. And here's what those values mean. So I have this continuum, this line over here. Over here I have +1, over here I have -1, and in the middle I have 0. Well, the closer that my number is to -1, the stronger my data is in the negative direction. So at -1, I'm going to have a strong negative correlation. As I get closer to +1, I'm going to have a strong positive correlation. So, if I get a correlation then of 0, that's going to tell me that there's no correlation. Okay, and -1 is the strongest negative correlation. +1 is the strongest positive correlation, and it gets weaker as you get closer to 0. We're going to look at some examples of that too that'll have it make more sense. Okay? So the next two are some processes that we do. So the first one is interpolation, and interpolation is when we approximate a value between two known values using its graph or equation. So when I think of interpolation, I think of the word interior. It means inside. So the way that this looks, right, is I have this graph here, right, these 2 points. And what interpolation says is that I'm going to approximate between these 2 points, okay? I'm going to guess or estimate what's happening in between those 2 points. On the other hand, extrapolation, so between is the important one here. Extrapolation, we think of exterior, outside. So extrapolation is when we predict a value that is outside of the range. So if I had the same line here, what extrapolation does, I'm going to color this in, so I'm approximating in the middle. Extrapolation, I want to know what's happening outside of this interval. And so that is what we would predict what's happening. Okay, so those are those two things. There's stuff that we do anyways that is just like a fancier way of saying it. And so it's not like vital that we know these specific words themselves, but it's good vocab to at least kind of talk about. Last one is causation. So causation is pretty straightforward. That's just when we're saying it's when a variable causes another to change. When a variable causes another to change. And think of this is just like cause and effect, right? We learn about cause and effect in English classes, we learn about it in science classes, also comes up in math class now too. So cause and effect. And then a couple things to note about causation too. So if I have causation, that means that what I'm working with has correlation. They're correlated to each other. Okay, and so if you think about like my example of as one value so like the more hours I work, the more money I get paid, right? So that would be an example of causation. the hours that I'm working causes me to have more money. On the flip side though, just because something's correlated does not mean that there's causation. Okay, something has correlation, that does not necessarily mean that it has causation. So think about a ridiculous example like shoe size and test scores, right? We would probably all agree that there is no correlation between shoe size and test scores. But let's just say that whatever data set that I'm working with, all of a sudden I gathered some data and it looked like there was a positive correlation between the two of them. It may be kind of slight, but there was a positive correlation. That doesn't imply that one caused the other. That doesn't mean that my shoe size caused me to have a better or worse grade. There just maybe is a coincidental correlation between the two. So causation implies that those two values are correlated, but correlation does not necessarily imply causation. All right, we're going to look at some examples of correlation coefficients. So I told you that we were going to look at some that would make have that make more sense. Oh, I did not spell that right. Hold on. Coefficients. Okay. All right. So we talked about correlation coefficients, and so this is what I mean, right? So this first example has a correlation coefficient of 1. All of these points lie exactly on the line. This is an example of strong positive correlation. Okay, the next one is a little bit more spread out, but I can still draw a line that goes through a lot of the points. I just have a few left on the outside. So there's still some positive correlation here, not quite as strong as the one before. And then we also have low positive correlation. You can still see that there's a trend in these moving upward. So I can still kind of draw a line of best fit in there. But the points are more spread out. So this would be an example of weak positive correlation. We're used to no correlation. That's just random dots placed places. Okay, and then the same thing happens with negative correlation. So this guy is trending downward, but we have it super spread out. So this is a weak negative correlation. This one's a little bit better, right? We've got more tight together, so it's a higher form of correlation. And then this last one is perfect correlation. So this would be strong negative correlation because it's trending downward and all those points lie on my line. All right, we're going to do some examples of using residuals. So the table shows the number of Y gloves sold for each amount X in inches of snowfall. The equation Y equals 1.5X plus 3.5 models the data. We're going to decide whether or not the model is a good fit. So I have my snowfall in inches first. Then I have the gloves sold. This is my actual amount. Then I would have my Y value from my model. That's my estimate. And then the last one is my residual, which if you remember is my actual minus my estimate. Okay, we're just going to work through this table. So when 1 inch of snow falls, I'm going to plug this into my line of best fit, which is right here. 1.5x plus 3.5. So I plug 1 in, get 1.5 times 1, which is just 1.5, plus 3.5 is going to give me 5. Do the same thing with 2. 1.5 times 2 is 3. 3 plus 3.5 is 6.5. I'm noticing that this is going up by 1.5 every time. So now I'm just going to go up by 1.5. So 6.5 plus 1.5 is 8. That's going to be 9.5. 9.5 plus 1.5 is 11. Next one's going to be 12.5. Last one, 14. Now what it wants me to do is calculate my residual. So I'm taking my actual minus my estimate. So 5 minus 5, 0. 8 minus 6.5, 1.5. 7 minus 8, negative 1. 10 minus 9.5 is 0.5. 11 minus 11, just 0. 12 minus 12 and a half, negative 1/2, and then 14 minus 14 is 0. So I could look at all of these and tell right away that this is going to be a pretty good model, right? But this is where I'm going to use an example of my total residual. So total, I did not, total residual is when I'm going to add them all up. So I'm not going to include the zeros, because if I add 0 to something, it's just going to stay the same. So my first actual number is 1.5 plus negative 1 plus 0.5 plus negative 0.5. Is that it? Yes. Okay, let's see. These cancel out and just become 0. So then I just have 1.5 minus 1 gives me a total residual of 0.5. That is very close to 0, right? So this is a good model. It's a good model. We're going to go ahead and look at what that looks like here. I think it's this one. Yes. Okay. So here is my scatter plot. These are the points that we created. We're going to go ahead and type in the equation that we were working with. So we've got y equals 1.5x plus 3.5. Okay, and we can tell right away that's a pretty darn good representation, right? You can see that the points on this graph are all very close, if not right on the line, right? There's just a couple that are a little bit further away. So this is a really good representation of our data. All right, let's move on to the next one. Oop, I think I went too far. Okay. Similar thing. Let's see. Snowfall, though, is going to change to, this is Mondays. And then this is going to be temperature. And then we're doing the same thing. This is my estimate. And then this is my actual minus my estimate. And we're just plugging these in. So here's the equation that I'm working with, y equals 7x minus 8. And I'm just going to plug these in. So you go ahead and plug those in, and you can check your answers with mine when you're done. Okay, so you should have gotten these values. We're just going to calculate a couple of these residuals, because I think you're going to see pretty fast why. So 48 minus negative 1, that becomes change, so my residual is 49. 43 minus 6 is going to give me a residual of 37. 42 minus 13 will give me a residual of 29. So on and so forth. I'll just fill these in and we can talk about it. It's pretty clear right away that this is not going to be a good representation, right? Are any of these numbers close to 0? No. None of these are close to 0. None of them are close to 0. So this is not a good representation. And we're going to look at that one too. Not a good model. So let's look at, it's my next graph here. Oops, I gotta zoom out. There they are. Okay. So here are my values that I just found. Okay, and we're going to type in the equation that we were given. Y equals 7x minus 8. Woof, that. Yeah, that is nowhere close to any of our points, right? Nowhere close. They're all super far off. So that is a terrible representation of our data set. Okay, let's see, last one here. This one should take not too long. Extend these down a little bit. I need to fix that in my note sheets. I wanted this to be a bigger table. Okay. I'm going to put an E here for estimate and an R here for residual. So we're going to do the same thing we just did. So go ahead and plug in your estimate values, figure out the residuals. You do not need to figure out the total residual, but figure out the residuals and then tell me if you think that this is a good model or a bad model. All right, so these are the values you should have gotten. All of these values are really close to 0, so that means that this is going to be a good model for us to work with. It's a good model for our data. Okay? Should feel pretty easy, should feel pretty straightforward. Let's move on then over here. Okay, so this is where I promised you technology. We're going to use technology to figure out equations of lines. So the table shows the number X of teachers and the number Y of students in each of several schools. So here's our data. We need to use a computer to find the line of best fit. So here we go. I want to go right here. All right. So here's what I did. This is a linear regression calculator. We talked about that linear regression was that process that computers use to figure out our line of best fit. I plugged in all of our data points already, so I'm just going to submit that. And what happens is my picture is not here. Let's try to refresh it. Is it going to show up now? Yes. Okay, perfect. So here are all of my data points, right? And it drew a line through those data points. So what this will tell me is my regression equation. So right here, it came up with my equation. Super long numbers, right? And I'm going to show you why. So this is the equation down here that they use to figure out what your line of best fit is, right down here, right? Which looks terrifying, right? That's what the calculator uses to figure out the line, which is why we are not doing that. And we are letting the calculator or the computer do it for us. Oops, I need to go the other direction. Okay, so let's go back up here. Okay, so our equation for our line then is 42-ish plus 21x. I'm going to flip that around because that's how we're used to reading it. So y equals 21x plus 42. That's the equation that it came up with. Okay? Now I want to know what is the R value or the correlation coefficient and interpret what that means. So I have a button down here, super nifty, correlation coefficient right here. So it calculated my correlation coefficient as being about 0.96. So I'm going to go over here and write that, 0.96. I want to show you this equation too because it's even more ridiculous than the other one. Look at that. Doesn't that look fun? That's what the computer is doing to figure out our correlation coefficient, which is awesome if you love math, probably terrifying if you don't. So, our correlation coefficient is 0.96. So if we remember the correlation coefficients, 0.96 is really close to 1, right? So this is going to have a strong positive correlation. So 0.96 means that it's going to have a strong positive correlation. Okay, next thing it wants me to do is interpret the slope and the y-intercept of the line of best fit. So my slope, in this case, is 21. And if you remember, slope means our change in y over our change in x. So my y values, if I look up here, my y values are all of my students. So I'm going up 21 for my change in y, and I'm going up 1 for my change in x in order for b to be a slope of 21, right? Because 21 divided by 1 is 21. So if I'm interpreting this in terms of my scenario, that means that when I add 21 students added, I need one more teacher. All right, y-intercept then, in this case is 42. Now, I want to think about what the y-intercept means. Okay, so if I have a graph over here, here's my graph, teachers is down here, students is over here. My y-intercept happens here at 42. What does that mean for my x value? So when I have 42 students, what is that? How many teachers do I have in this case? I've had several people tell me today that they would have 2, because we said for every 21 students you need 1 teacher, so you would need 2. But that's not what this is telling us. If I were to ask you to tell me what this point on the graph is, this point is 0.42, because we know that our y-intercept happens when x equals 0. So what this is actually saying is that in theory, if we had 42 students, we wouldn't have any teachers. Is that realistic? No. Does it sound awesome? Maybe. But it's not, it does not make sense in our context. So our y-intercept in this case doesn't make sense. And we're going to talk about that. So it doesn't make sense in context of our problem, but that doesn't mean that it's wrong or that it's bad, right? So what the line of best fit does is it takes the data that we have been given, it assigns a line to it, not taking context into relation at all, right? All that the computer sees is numbers. The computer doesn't see that we're talking about students and teachers. All the computer sees is 10 goes to 250. 12 goes to 275. 13 goes to 312. It doesn't have any other context other than just the numbers. So this is still our line of best fit. This does represent our data well. But the y-intercept in this case does not make sense in terms of our problem, and that's okay. Okay? So that's what we've interpreted all those things. Okay. So now we're gonna interpolate and extrapolate data. So interpolation means that we're going to look on the interior. We're gonna estimate with things that we have been given. Extrapolate means we're gonna predict what's going to happen later. So when there are 366 students, well, I know that students is y. How many teachers am I going to need? So 336 equals 21x plus 42. Now I know I just need to solve for x. So subtract 42 leaves me with 336 minus 42 is going to give me 294 equals 21x. Divide both sides by 21. That means that x equals 14 teachers. So when I have 336 students, I need 14 teachers. Next one is predict. So first one was approximate. Now we're predicting. This is extrapolation. When I have 20 teachers, how many students should I have? Well, I don't know what y is, but I do know that I have 20 teachers in this case. So then I would just multiply these out. 21 times 20 is 420 plus 42. So that means that y would need to equal 442. Oh, wait, hold on. Yeah, 462 students. Now here's the difference between these two. So I know that there are 336 students. I know that. And so when I'm approximating how many teachers fall in that range, that's interpolation. That's when I'm taking something on the interior and predicting what's happening on the inside. Extrapolation is when I'm predicting. I'm going to see, well, if I have 20 teachers, then how many students would I have? Would I predict that I would need to have in order to get there? So that's the difference between those two. Okay, almost done. Now we're going to talk about correlation and causation. So here's an example. Time spent babysitting and the amount of money earned. First of all, are these two things correlated? Second of all, do they have causation? Does one cause the other one to happen? Well, time spent babysitting and the amount of money earned would have a strong positive correlation, wouldn't it? It's my example of the more hours you work, the more money you have, right? It's going to have a strong positive correlation. This also has causation. The hours that I work cause me to have more money. Hours worked causes you to have more money. So this is an example of something that has correlation and causation. It's strongly positive correlation and it has causation. Let's go ahead and look at one more example of this. So, eating organic food and getting a good score on a test. Well, here's the thing with this one, right? This one may have slight correlation. And let's just think about this, okay? So it may have slight correlation in the positive direction, because if you're eating good, you're probably feeling good. If you're feeling good, then you'll probably do better on tests, those kinds of things, right? But there's no like direct correlation between those two things. So it may have a slight correlation, but it's not going to have any sort of causation. Eating organic food does not cause you to do well on a test. Okay, if we were talking about something like hours studying, that would probably have some causation, right? You spend however many hours studying, you do better on a test. That has some causation because one causes the other. But just eating organic food and getting a good score on a test, that is not an example of causation. One of those things does not cause the other one.